All right, check it out. Guys, I've got a solution of sodium potassium tartrate in water sitting in this beaker with my little wonderful little spinny thingy there so I don't have to stir it. It's awesome. And what I want to do to it is I want to add some hydrogen peroxide to it, because the hydrogen peroxide should be able to oxidize the tartrate ion into some methanoate ions and some carbon dioxide and some water, and it's a really cool reaction. Watch what happens when I add my hydrogen peroxide to the tartrate solution. Wow, that's exciting, right? So before you turn off your camera thinking this is the dumbest demo in history, just give me a moment. So believe it or not, there actually is a reaction happening here between the hydrogen peroxide and the tartrate ions, but the problem is it's very, very slow. Hi everyone, and welcome to this episode. Today, you just saw me mix two chemicals together to do a dud of a reaction that was moving really slowly, and I'm sure it was really super boring for you, so I apologize for that. But we're going to try to fix that, and we're going to try to fix it by thinking about successful collisions, activation energy, and the role of temperature and catalysts in that activation energy. So if all goes according to plan, in a few minutes, you'll not only understand all of that, but we'll also get a better reaction out of it. So let's get going. Let's talk about successful collisions, because in chemical kinetics, it's all about the collisions. Molecules have to collide with each other in order to react with each other. They can't do it from across the room or across the field or across the world. They have to collide with each other and be able to break bonds or exchange electrons or exchange protons, whatever it is they're doing. And for a successful collision to occur, molecules must collide with each other with two criteria. One, enough kinetic energy to begin breaking and reforming chemical bonds. Just a gentle little nudge or a tap is not going to do it, people. Bonds break, protons get exchanged, electrons get exchanged, that kind of thing. So they have to be moving fast enough. And second of all, they have to be oriented properly. So in a molecule, there's usually one end or one part of a molecule that needs to actually connect with the part of another molecule. And if they're not arranged in the right orientation, they will not actually react. And let's talk more about that kinetic energy briefly. We have a fancy term for that, as we do in chemistry class for a lot of things, and we call that activation energy. And activation energy, I have a couple of definitions on my slides, so if you want to pause them at all and take notes, you totally can. Activation energy is the energy required for the reactant molecules to get to their transition state and then proceed toward the product molecule. So you imagine, and the transition state or activated complex is the higher energy state that exists when molecules are in the process of breaking bonds and forming new ones. So imagine you've got your reactant molecules and your product molecules, but there's usually somewhere in the middle there where they're transitioning. They're not the reactants they used to be. They're not the products they're going to become. They're transitioning, and that can be a stressful situation. And so they're at a higher energy state for that brief instant of time. That means extra energy has to go in to get them there. Once they're there and past that state, they move toward making the products, and then they give that energy back and to some degree or another, and then they end up at some final amount of energy. All right, and this is a reaction profile that shows the relative energies of both the reactants and the products, as well as the energy needed to get to that activated state or the transition state. So we have a couple of words for that. You'll see these a lot in your chemistry travels. And so my job in this video is to help you just navigate those and even sketch them yourself. So here's that energy diagram again. On a reaction profile, is one way to call it, the activation energy is represented by the difference between the given starting point and the top of the hill on the graph. There's like a little hill they got to climb and get back down to the bottom on the other side to reach the promised land, so to speak. And the top of the hill, that's just represented as how high the hill is how much activation energy it has. It might be unlabeled as a general graph, or it might be labeled as, in this case, 132 kilojoules for every mole of reactant. Okay, and the enthalpy change, you might recall, tells you whether it's exothermic or endothermic, and it's represented by the difference between the starting value and the end value, regardless of how high the hill is or how many hills there are in the middle there. The difference between start and finish, that's your enthalpy change. Okay, so I'm going to show you a couple other quick examples before we have a couple of pause the video moments. In this example, there are 2 peaks, and they represent 2 steps in the reaction mechanism. So you may have learned about reaction mechanisms already, like reactions happen in sometimes many steps. And in this case, there's 2 of them. The reactants and products, you have to go up this mountain down to the middle, and that middle part right there is a place where we would have a reaction intermediate. A stable species that's not the reactants anymore, but it's not quite the products yet. Maybe it has another step to go, but it'll get there. And that's where the intermediate would sort of live on the energy diagram. And we have this 2-part thing. The first step has the largest activation energy. The difference between start and the top of the mountain, that's EA1. And that means that's probably the rate determining step. It's the slowest one because it has the biggest mountain to get over for those little molecules to do it. The second activation energy is much smaller, just a little nudge to get it over that second hill, and then we're back to the products. And this reaction is endothermic because the difference between start and finish is actually a positive value. Delta H equals a positive value of some kind. In this reaction profile, there are 3 different peaks, and that represents a reaction mechanism that might have 3 steps to it. Step 1, step 2, step 3. And overall, the reaction is exothermic because we're going down from start to finish. So the delta H is going to be some negative value. Again, it's not labeled. We're just thinking generally here. But the molecules have to have a first activation energy in order to get to transitions intermediate, reaction intermediate. Sorry about that. Apologies. And then we have another reaction intermediate as right in there. But we have a couple of activation energies. Each step has its own activation energy. This last one being nice and small. So once we've become in reaction intermediate, okay, we're kind of at rest here. We're in a nice stable spot, but then we need another kickstart to get over the next hill. So that would be the second activation energy. It's hard to tell which one of these is bigger, so it's hard to tell which one is the rate determining step. But, with more information, we'd be able to determine that. Okay, so in your chemistry travels, if you're taking a chemistry class with kinetics in it, you're probably going to be asked a question something like this. And we're going to do a couple of pause the video moments coming up if that gets you excited. So a 1-step reaction has an activation energy of 134 kilojoules per mole and an overall enthalpy change of minus 46. Sketch a reaction profile for this reaction. So here's what you want to do. You want to sort of give yourself some space to work. Give a couple of axes here. You can even label it if you want, like which direction the reaction's going. You could even label this with an E if you wanted. Lots of times it's not even necessary. You're thinking generally here, just visually. And okay, so we're going to pick a starting point. Now I know my overall reaction is going to go down 46. So I'm going to just set up my start and finish. Reactants over here. Products over here. If you actually know what the reactants and products are, like for example C3H8 and O2, you can actually put their chemical formulas there. It's actually very helpful. And I know that I need to end up 46 kilojoules less than what I started with. Sorry about that. And that will get me that. Now I also have to have a 1-step, 1 mountain or mountain peak to go over, and I got to represent as best I can 134. So I'm going to make this bigger than this little drop. And then we'll head back down here. And I'll label the activation energy, which is EA, and that's going to be 134 kilojoules. Okay. You might even be asked, what's the activation energy for the reverse reaction, going back the other way? And it might make sense to you that if I started here, let's pretend I'm there. There's a little stick guy me. And I need to get back up here to the reactant side. I have to go up this huge, huge mountain, which is actually the sum of 134, which I got back from the activation energy, and the 46 that ultimately was given off. So you just add it up in reverse to go over the top. Okay, you try. We're going to do a pause the video moment for a similar question. A 1-step reaction has an activation energy of 75 kilojoules per mole and an overall enthalpy change of 25. Sketch a reaction profile. So pause the video and see if you can do that. We'll check in 1 second. Okay, if you were able to come up with a reaction profile that looks kind of like mine. It won't look exactly like mine. They don't have to. We're not looking for fancy artistic skills here. We're just a visual generalization of what's going on. You should have a hill that's about 75 kilojoules tall, and you ultimately end up higher than you started at plus 25. So the activation energy for the reverse reaction, going back that way, would be 50. 75 for the forward reaction, and then only 50 to get back up over the hill in the reverse direction. So good job on that. All right, we're going to do one slightly fancier before we wrap things up and talk about my reaction again. The first step in a two-step reaction mechanism is the rate determining step. Thank goodness they told me that. Great. With an activation energy of 120 kilojoules per mole. The overall reaction has an enthalpy change of plus 30. Let's sketch a reaction profile. So again, not really trying to be artistic here. Let's give ourselves some space to work. And I'm going to say plus 30. All right, so I'm going to start low with my reactants. And I'm going to end up plus 30 with the products. Okay. In between, I need 2 peaks because it's a two-step mechanism. The first step has an activation energy of 120. So this is going up 30, so let's go up approximately 4 times that. Could be. And then we're going to kind of crest that first peak. And then what we need to do is add a second peak. Now, because this is the rate determining step, it's got the biggest activation energy. I know the subsequent steps are going to be smaller than that. So EA, I'm not told what they are, but let's just put another little peak somewhere in the middle there and end up at our products. Again, not the most beautiful diagram in the world. So delta H is positive 30, and the EA is 120. So 2 peaks and some similar data. Okay, you try. Here is example number 6. See if you can pause the video and come up with a reaction profile that would show this 50 and 75 kilojoules. All right, if you paused the video and did that, congratulations, and hopefully you came up with something that looks like this. The original activation energy is up 50, but we're ultimately going down 75 with another hill somewhere in the middle. Doesn't matter where you put it, but somewhere in the middle at a lower height, and we get a reaction progress that looks something like this. But let's get back to our demo that we were working with before. How could we're going to ask this question, how can we increase the number of successful collisions in my beaker that was sitting there doing not a lot? Okay, there's 4 ways, and you might want to write these down. You can, number 1, increase the concentration of reactant molecules. Just cram them in there. Get a higher molarity solution. You can shrink the balloon. You can shrink your container. Ultimately, raise the pressure of this thing. Get them colliding with each other more and more often, and that generally increases the rate of reaction. I'll skip to 3. You can increase the surface area exposed to the reaction. Just get them in contact with each other, stir them around. You can increase the temperature of reactants, and you can add a catalyst. I want to talk about these 2 and 4. So one of the ways that you can speed up a chemical reaction is by heating it. And when you heat it, the molecules have more kinetic energy, they collide with each other more frequently and with more force, and typically you get a faster rate of reaction. But even up here around 60, 70 degrees, I'm really not getting a very fast reaction. I'm not seeing very many bubbles at all, which is what I was hoping for. Okay, this is very common and very important, by the way. And what this shows is a distribution of the number of molecules with a given energy at a certain temperature. Each one of these curves represents a temperature. The red one is higher temperature. Now, at any given temperature, there's a few molecules with very little kinetic energy. They're barely moving at all. They've been bounced around, but they're hanging for just a second. There's a few molecules with very high kinetic energy, and a lot of them are kind of just in the middle, somewhere near the average. In the reaction profiles, the activation energy is represented by a peak on the graph. On this one, the activation energy is represented by a line, a vertical line here, showing some minimum energy each molecule needs to have. And anything beyond that has fulfilled the activation energy and then can go forward with the reaction. When the temperature is low, there's going to be very few molecules in this area shaded that have enough energy to do the reaction. But if you crank up the temperature, the whole mountain shifts to one side, and now the average is higher than, say, here than there, and you've got more molecules with a higher average kinetic energy, and a larger portion of this shaded under the curve that's beyond the activation energy. So more molecules with enough energy, the faster the reaction's going to go. And finally, the fourth thing I could do to speed up a reaction is add a catalyst. And catalysts work in a few different ways. One of the biggest ways they do that is by lowering the hill. They lower the activation energy that is needed for those molecules to exist. And this, what I'm holding here, is a solution of cobalt-2 chloride in water. Cobalt-2 ions have this nice reddish, pinkish color to them because the way they reflect wavelengths of light, and that's really cool. But cobalt will actually act as a catalyst for this reaction, and we'll get that into a beaker. Oh. All right, check it out. We have a color change, and oh, that's awesome. So something is definitely happening here, right? And something that wasn't happening before, I added the cobalt. I can sense the bubbling starting to slow down here a little bit. Not getting as much of that. The temperature has gone up a little bit during the course of the reaction. We're up around 74 right now. And check it out, and check it. So now we're back into the pink color that was originally from the cobalt ion. And in the middle, we had this green color. Okay, so what was that all about? One of the criteria for being a catalyst is that the catalyst itself is not a part of the reaction. It's not used up in the reaction. And in this case, the cobalt ion goes from +2, which is pink, to +3, which is green, and at the end of the reaction, it gets its electron back, and now we're back to being green again. So the cobalt is still there. It did not get used up in the reaction, but it certainly helped the reaction along.